Hello, thank you for joining us. This is lesson 1.5, angle addition. The objective of this lesson is to use angle addition postulate to use the angle addition postulate to find angle measurement, and use the angle addition postulate to create and solve equations. We'll use to find also maybe some angle measurements as well. So let's go straight into it. First of all, let's discuss what an angle is. An angle is simply turning around a center point, having a point and turning it, and created by the in the forms by two rays, like as you see in the diagram below you. All right, we have this line. We're going to again rotate it to turn it and create another line around this center point or this corner point right here called a vertex. So like I said, this center point is referred to as the common point. What we're turning is called the vertex, and an angle is formed by two rays with that common point, with that, again, center point. The rays are referred to as the sides of the angle, and the way that we name the angle is using simply the vertex or the three letters, the three dots that create that angle from the center to the sides. So for example, on this angle right here, we can name this angle B, simply using the vertex, or we can use again the 3 points that create this angle, and again in the following order: angle ABC, angle ABC, we create this angle going downwards, or angle CBA, which creates this angle going upwards. Regardless of the direction, these two angles are the same because they both measure a total of 60 degrees. Now, the way that we describe and the way that we indicate that we have the measurement of angle is that we use the letter M for measurements. This symbol here is the symbol for the word angle, and we can say that the angle ABC is equal to 60 degrees, as the same as saying the measurement of angle CBA is equal to 60 degrees. And of course, we can also say that the measurement of angle B is equal to 60 degrees. They all mean the exact same thing. Now, there are 4 types of angles. You have your straight angle, which measures exactly 180 degrees. You have a right angle, which measures 90 degrees. An obtuse angle that measures more than 90 degrees. And an acute angle, which measures less than 90 degrees. Now, for the obtuse and acute angle, we're not certain. Again, it could be anything as long as it's 90 or less than 90 degrees. But for the straight angle, it equals exactly 180 degrees every single time, and a right angle always measures 90 degrees. But an obtuse angle is never going to measure the same thing every single time. It's just going to be for certain that's going to be a number that's greater than 90, and the same thing is true for an acute angle. All acute angles are not the same measurements, but they are going to be an angle measurement that is less than 90 degrees. So for example, 45 degrees is an acute angle, just like 60 degrees is an acute angle. An obtuse angle, the same thing. 110 degrees is an obtuse angle, just like 91 degrees is an obtuse angle, because both of those numbers are greater than 90. Now let's go over an example of how to name and identify the sides, or to identify the parts of an angle. And we're going to begin again with the vertex. The vertex of an angle, again, is the center point of the angle. So in this case, if this is the angle going in this direction, upwards or downwards, or from left to right, okay, the center point, K, is referred to as the vertex, while the two sides, K to L and K to J, those two sides are referred to as the sides of the angle. And just like the other angle, there's three ways of naming this angle. We can name this angle either angle K, or we can name this angle JKL, which is going in that direction, creating this angle moving in that direction. Or we can name the angle going in the opposite direction, starting off with letter L, going to letter K, and going to letter J. K, L to K to J, creating this angle going in that direction. The one thing you can notice is when we use the letters, the points that create the angle, you're going to notice that the vertex in both of them is always in the middle. And that's always going to be the case. Just like in the previous example over here, the vertex always has to go in the middle when using the three letters or the 3 points that create the angle. The vertex always has to go in the middle. Because again, you're going in the direction of the letters. If you start off with B, go to A, and go to C, you're creating a different angle. That refers to this top angle right there. And if you start with B, go to C, and then go to A, again, that refers to a different angle right there. So when you're naming the angle using the 3 letters, you always have to make sure you place the vertex in the middle, because that's the direction you're moving. You're moving from one endpoint to K to L, creating this angle going downwards, or you're creating the angle JK to L going upwards. They're the same angle, of course, but we're just using a different name to refer to the angle. Now, some characteristics about angles is that we can divide an angle into 2 equal parts. If we do that, we use something that's called an angle bisector. An angle bisector is simply going to be a line or a ray that divides an angle to 2 equal parts. Your right angles, if cut into 2 equal parts, because they always measure 90 degrees, will be 45-degree angles. Those 2 angles will always measure to 45 degrees. If you have a straight angle and it's cut by an angle bisector, then the 2 angles are always going to be 90 degrees. Because again, a straight angle measures 180 degrees every single time. With an obtuse or an acute angle, again, it will depend on what the angle measurements are in order to know what the 2 sectors, what the 2 angles are when you cut it by the bisector. So like this one, it seems like this entire angle measures a total of 40 degrees, because this was cut into 2 equal parts where the 2 measurements are 20 and 20 is 40. Which brings us to our next characteristics about angles, which is the angle addition postulate. The angle addition postulate states that if we have an angle, let's say angle A to B to C, okay, this angle right there, angle B, all right, which is this angle B right there, we can figure out the measurement of this big angle right there by adding the sections in between. So it's very similar to the segment addition postulate, but we're just using angles now. So if I add the orange and the purple section together, it's going to create this big angle from this side to this side. So this big angle right there, which is what this is saying right here. That angle A, B to D, the orange one, plus DB to C, the purple one, add up to create this red angle from using side BA and BC. Creates that angle ABC or CBA, going in that direction. Now, before we look at some examples of the angle addition postulate, let's go over 2 other things. Perpendicular lines. Those are lines that intersect to form a right angle. Now, any 2 lines can intersect in various ways, but if they intersect and they create a 90-degree angle, a right angle, as you see right here, those 2 lines are perpendicular to each other. So those 2 things go hand in hand, all right? We create angles that are 90 degrees. Now, if we have a perpendicular bisector, it does two things. Not only will it create a 90-degree angle, but the bisector portion of it divides the segment into two equal parts. So a perpendicular bisector is going to be a line that divides a line segment into two equal parts at a 90-degree angle. So these perpendicular bisectors, again, divide the segment, not the angle, but the segment into two equal parts and intersect at a 90-degree angle. Like the way you see right here, this diagram right here, when we have a horizontal line and a vertical line, this two sides would be equal to each other and we have a 90-degree angle. I know this is probably not a good illustration, but right here, by having this perpendicular bisector creating this 90-degree angle, it's a perpendicular bisector if these two sides are equal to each other. And the same thing right here. These two sides would have to be equal to each other to be a bisector. So again, it's two things that happen with a perpendicular bisector. And we have perpendicular. Perpendicular just makes the angle of intersection 90 degrees, but the perpendicular bisector makes the angle of 90 degrees, as you see in the three illustrations, but also cuts the segment into two equal parts. And this right here technically should be endpoints. This should not be a, let me close those. Yeah, that should not be a line. Those should be an endpoints. So now let's look at some examples of how to use the angle addition postulate. So again, the angle addition postulate simply states that if I get this section here and I add it with this section here, okay, that's going to create the measurement that would equal to the measurement of the entire angle from this side and this side where the vertex is right there at B. So adding those two is going to equal to the measurement of angle A to B, vertex B to the C. Well, let's see what we have here. According to what's given to us, the measurement of ABD, which is the orange one, is 48 degrees. So this is 48. And the measurement of DBC is 78. DBC, the red one, is 78. So adding those two, is going to equal to the measurement of the purple, the entire angle. So, well, 78 plus 48. That's equal to 128. So the measurement of angle ABC is equal to 126. Again, degrees, 126 degrees. Let's look at our second example. Again, same concept, using the angle addition postulate, that if we add this orange section with this red section, that has to equal to the angle measurement from A to B, B to C. Adding those two will equal to the measurement of angle A, B, C. Well, the measurement, they're telling us that the measurement of angle B, D, the measurement of angle DBC, sorry about that, is 74 degrees. Well, D, starting at point D to point B to point C, is this red angle. That's going to be 74 degrees. And the angle measurement of ABC, which is the entire thing, this large angle right here where the vertex is B, that's 119. So according to the segment addition postulate, adding the orange one, which we don't know, plus the 74 has to equal to 119. So I can come up with an equation, and instead of using a question mark right there, I'm going to use a variable x. So if I get x, the orange one, added with the 74, the red one, it has to equal to the measurement of the entire thing, which is 119. Well, solving this equation, I just simply need to have my letters to the left, my numbers to the right. I get that x is equal to 119 minus 74, and 119 minus 74 is equal to 45. So this has to be 45 degrees. Now in our third example, our equations are becoming a little bit more complicated, but the idea again is still the same. In order to use the segment addition postulate, if I add again the two angles next to each other inside again, they have to equal to the measurement of this big angle from point D to point E, vertex E to point F, okay? When it's split up by this segment, by this ray from E to G. So if G is in the interior, I can add the orange angle with the red angle to create that blue angle. Well, the blue angle, which is D, E to F, that's equal to 7x plus 4. So adding the orange and the red should equal to 7x plus 4. Well, let's see what the orange is. The orange is from point D, E to G, which is 5x plus 8, plus 1, I'm sorry. And the red angle goes from G, E to F, or F, E to G. Again, doesn't matter where you start, whether G or you start at F, but E has definitely have to be in the middle. This angle right here in red, that's equal to 23. G, E to F, that's 23. So if I add those two, that has to equal to 7x plus 4. Well, let's see, let's add those two before we equal it to that, so we can come up with a simplified form of the equation. Well, I cannot add the 5 with the 1. I cannot add the 5 with the 23, but the 1 and the 23 can be added together to get 24. So 5x plus 24 is going to equal to 7x plus 4. Let me move this up here. So solving this equation, we would move our letters to the left, our numbers to the right. And we get that negative 2x is equal to negative 20. We would divide then by negative 2, and x would equal to positive 10. So we now know that the value of x is equal to positive 10. Now this is not the only thing that we're interested in finding. We are also interested in figuring out the measurement of angle DEG. Well, looking up here, DEG is equal to 5x plus 1. Let's make this smaller and move it down here. The measurement of angle DEG is equal to 5x plus 1. Now that I know that the measurement of x is equal to 10, I can multiply 5 and 10, add 1, and that's going to equal to 51. So that angle measurement is equal to 51 degrees. Now we still have one more angle to find. We want the measurement of angle DE to F. DE to F. That's given to us to be 7x plus 4 degrees. So we're going to replace again the x with 10. Multiplying 7 and 10 and adding 4 gives us 74. So we have 74 degrees for that angle measurement there. On our fourth example, a little bit more of the same. We're going to be another example of how using the angle addition postulate. Let's begin with the main idea that the angle addition postulate says that if we have this major angle which we will do in blue, from J, highlighted blue, from J to K to L, and there's this interior M that gets connected from the vertex. Well, by adding those two sections, which I'm highlighting in orange and in red, that would equal to, again, the measurement of JKL. Well, the measurement of JK to L, JKM, MKL, JKL, that one right there, is 10x minus 11. So adding the orange and the red, that has to equal to 10x minus 11. Well, let's see what the measurement of the orange one is. Well, the orange one uses the letters J, K to M. J, K to M, that's 43. So this is equal to 43 degrees. The red section, which is from letters M, K, L, the name of that angle is MKL or LKM, where K again is in the middle, that's equal to 8x minus 20. So by adding those two angles, the orange and the red, by adding these two angles, that has to equal to 10x minus 11. So that's how we're going to create and set up our equation. Well, I'm going to again simplify my like terms. 43 can be combined with 20 because they're like terms, and we get that 8x plus 23 is equal to 10x minus 11. So moving our variables to the left and our numbers to the right, we get negative 2x is equal to negative 34, and dividing by negative 2, the value of x is equal to 17. So there, we found that the value of x is equal to 17, and we can now use that information to figure out the measurement of the following two angles of MKL and JKL. We'll start with the top one. Well, MKL is here, and according to the information that's given to us, that's provided to us, that's 8 times x minus 20 degrees. Too many parentheses, so we get confused. Well, 8 times 17, that's equal to 106, no, 136. I was off by 30. And then 136 minus 20 is equal to 116. So the first angle measurement is 116 degrees. We now want to figure out the measurement of JK to L. JKM, nope, that's 43. Already know that one. We want this angle measurement, JKL. That's equal to 10 times x minus 11 degrees. Well, substituting again 17 for the value of x, we'll get 170 minus 11, which is equal to 159. So that's the angle measurement of JKL. And then finally, moving on to our last example. This one's going to require to do again multiple steps because we have a lot of information on this example. And we'll begin by first looking at what's given to us at the very beginning. And it starts off by stating that the ray BD bisects angle CBE. So BE being the vertex, so CBE, this angle right here, is cut into two equal segments, or I'm sorry, two equal angles using that bisector from point B to D, that ray right there. Well, what's so interesting about being bisectors or having a bisector is that those two angles are going to be equal to each other. So this yellow line is going to equal these two angles, which I'm going to color in orange and in red. So the orange and red angles are equal to each other. Now, the next thing that we're given, which I'm going to highlight in green, is that ray BC is perpendicular to ray BA. So the ray BC and ray BA intersect at a 90-degree angle. This is the symbol for perpendicular. So this is going to be a 90-degree angle. Which again is indicated by the square. So I'm just going to write 90 degrees. So I'm going to highlight that angle in green, okay? So we have that angle right there in green. Now the next piece of information that's given to us is that the angle, measurement of angle CBD. So let's find that over here. So from point B to vertex, from point C to vertex B to point D, which is the orange one, that's equal to 3x minus 25. So let me highlight that in orange. And let me actually, you know what, let me just write it there. That angle measurement is 3x plus 25. The next information that's given to us is that the measurement of angle DBE, so let me find point D to vertex B to point E, which is the red angle, that's equal to 7x minus 19. 7x minus 19. So let me just write that. So they give us all this information, and now what they want us to find is to find the angle measurement, the measurement of angle ABC. So they want to figure out the measurement from point A to vertex B to D. So they want to figure out the measurement of these two angles right there put together. So the measurement of this, is going to be the summation of the green and the orange angle. So I need to add, this is what I'm trying to do. Let me put a little star right there. I want to get the 90 and I want to add it with 3x plus 25. That's going to equal to the measurement of angle ABD. By adding this angle and that angle, that's going to give me the angle measurement from point A to vertex B to point D. But here's the problem. I don't know what the value of x is. I don't think they want me to give you the expression. They want the measurement. So I'm pretty sure they want the actual numerical value. And I do not know what the value of x is. I can add the 90 and the 25 to simplify this, and I'm going to get that 3x plus 115 is equal to the measurement of angle ABD. But that's not what they want us to do. Okay, so I have to look at something else. Well, I have a lot of other information I can use. The other thing that I know is that the orange angle and the red angle are equal, because that's what the first thing that I got. That this yellow line that I just highlighted it in blue is the bisector. So the orange and the red angles are equal to each other. So let's see how that's helpful. So if I get the red angle of 3x plus 25 and equal it to the red angle of 7x minus 19, I come up with an equation that I can solve to figure out the value of x. And then figuring out the value of x, I can plug it in and then figure out the measurement of angle ABD. So let's do that. Let's figure out the measurement of the value of x. So we're going to move the x's to the left, the numbers to the right. That gives us negative 7x. That gives us negative 25. And we get that negative 4x is equal to negative 44. Dividing by negative 4, the value of x is equal to 11. There. Now that I know that the value of x is equal to 11, I can now plug it in to my x here, and I can figure out the measurement of angle ABD. So let's plug it in. So we have 3 times 11 plus 115. 3 times 11 is 33. Add that to 115, and that's going to equal to 148. And there, we found our solution. And yes, this last one was a little bit harder than the other ones. It required us to use some bisectors and some other pieces of information to put it all together. But ultimately, we still ended up using the angle addition postulate there. We added the 90, the green angle, with the orange angle, requiring us to substitute in the value of x, to give us again the angle measurement of ABD. Well, that concludes this lesson. Again, I hope this was helpful. And like usual, again, thank you for watching, and hope you see you next time.